Okay, good morning, students. Today we will discuss our second unit, that is chip design method. The second unit is basically divided into two parts. First is chip design method, and the second one is the design capture tool. So first we will discuss about some chip design methods. Then later on we will move towards the design capture tool. Okay, so in today's lecture we will discuss some different types of synthesis method, or we can say some types of level designing that we used when we want to design any chip, any integrated circuit. Okay, so when we design any integrated circuit, so it can be divided into various levels. Out of them, some are such as behavioral, RTL, logic, structural, layout. These are all the designing levels. So we start from behavioral level, and then we will move towards the RTL, logic, structural, tool, layout, and so on. Okay, so let's start our topic. First behavioral synthesis. We will start behavioral synthesis. So before starting this topic, first we have to know that what is the mean of synthesis. Synthesis is nothing but a transformation. Synthesis is nothing but a transformation. It is generally used when we want to transform any type of designing function into a terms of structure. Okay, when we transform any function into a form of structure, then it is known as synthesis. Okay, when we convert it into in the form of a structure, then in the form of a structure, it is the combination of various logic components and interconnections. Okay, so conversion of function into a form of a structure is known as synthesis. Okay, so there are the various level through which we can start our chip designing process. It can be top to up approach, or up to it can be divided into bottom up, or up to bottom, top to bottom approach. Okay, in first we when first we start behavioral synthesis. Behavioral synthesis is also known as high level synthesis. Behavioral synthesis is also known as high level synthesis. It is mainly started from 1990. It is mainly started from 1990. One of the company name as Mentor Graphics used this behavioral structural behavioral design for their commercial chip designing process. So later on, several other companies will decide to implement their chip by using this behavioral synthesis process. Okay, so this behavioral synthesis, it in its original form simply provided a time and resource abstraction. This behavioral synthesis simply provide some time and resource abstraction. It is differ from the logical synthesis. It is differ from the logical synthesis. We already know that behavioral synthesis is also known as high level synthesis. Behavioral synthesis is also known as high level synthesis. So this high level synthesis is differ from logical synthesis. There is some difference between the logic synthesis and the high level synthesis. What are these differences? In logical synthesis, for the designing, we start from boolean expression. And we will move towards the gate function. Okay, now it is clear to all of you. In logic synthesis, we start from the boolean expression. And move towards the gate level design. Clear? But in logic level synthesis, the designing starts from the behavior of the element. The designing basically start from the behavior of the element, not with the boolean expression. Okay, in logic synthesis, designing start from boolean expression, but here the designing start from the behavior of the circuit, behavior of the element. Okay, but we can say it is start from the more abstract level, but we can say it start from more abstract level. Now what is the mean of abstract level? Suppose primarily we know that the smallest element of any integrated circuit is the transistor, and by combining the various type of by combining various transistor, we implement some gate level structure. By combining various transistor level, we implement gate level. So if in our circuit the number of elements are very less, so we can analyze it, we can synthesize it by using a transistor. We can synthesize by using a transistor because number of transistor are very less. But if the quantity of transistor increases rapidly, if the quantity of transistor increases rapidly, because the complexity of the circuit increases. So that what we can do, we can start from gate level instead of using transistor level. Okay, so when we start designing gate level, it means that we implement a circuit by using some digital logic gate instead of using transistor. If we implement the circuit by using the gate only, so it is under the category of gate level synthesis. Okay, so when number of transistor is high compared to transistor level, so we cannot start our designing process in transistor level, because the number of transistor are very huge as compared to transistor level. At that time it is suitable for the designer to start from gate level. But when the number of gates are increases in the circuitry because of the complexity of the circuit, so what can we do? We can't start from the gate level at that time. So what we can do, at that time we start the circuit synthesis by using the RTL level, because if we start synthesize of circuit by using gate level, so it is very time consuming process. So it is beneficial for the designer to start from the RTL level, and later on it move towards the abstract level if the number of RTL levels are higher. Then we can't use the RTL synthesis to implement the circuit. At that time we move towards the behavioral level, or we can say abstract level. Okay, so these all are, that is transistor level, RTL level, gate level, behavioral level, layout level. These all are the synthesis level. That means how can we start our circuit, how can we start our circuit for the implementation. Okay, you can understand the behavioral level, by using this example as uh, if a computational required five if a computational wait if a computation requires five add operation that are independent of each other, so it could be done in one cycle. If there were five adders available, or five cycles if there was just one adder available. It means that according to the requirement of circuitry, according to requirement of operation, according to requirement of demand, in behavioral synthesis, the designer can implement their design. It means that if there are five different adders, this example shows that if there are five different adders, and they all are independent. So in only one machine cycle, all provide their output, and we can provide their output to some other operations, because they all these adders are independent. So output of one adder does not affect the output of another adder. So we can start the adding operation simultaneously in all adders. But when these are dependent, when these all adders are dependent, it means that when output of one adder affect the output of second adder, then at that time we can start this all addition parallelly. Okay, so all these timing abstraction, all these timing limitations, limitations can be provided in behavioral synthesis. Okay, behavioral synthesis uses a high level untimed, partially timed, or functional description. Okay, there were several reasons why behavioral synthesis were not successful. Behavioral synthesis, this type of synthesis process is not very successful. It only start from 1990s, but later on no company uses this type of synthesis. The Because of unsuccessful, there are various reasons. One of this is language dependency. This is shown here. One issue to not use the behavioral synthesis uh, is the dependency of language in all commercial, because in all commercial process, in all integrated circuit that used in that time uses the Verilog language or VHDL language as their input language. It is already mentioned here, because that is the natural choice. Indeed, probably the only probably this one is the only choice at that time, that the designer can use the Verilog language, or they use the VHDL language for their designing process. So what we done if we done behavioral synthesis at that time. So at that time, for behavioral synthesis, first we implement our whole program. First we implement our designer's demand in the form of C or C++ language. We implement the algorithm in form of C++ language. Then later on we convert then later on we convert this C or later on we convert the algorithm that is written in C or C++ algorithm into a form of into form of VHDL or Verilog language. So this one is the some awkward procedure. So this one is very awkward procedure. That's why the designers are not using the behavioral synthesis. Okay, another reason why behavioral synthesis not used, uh, that the difficulty with timing, that provided in the behavioral synthesis is also one of the limitations. Of a behavioral synthesis. Okay, this is mentioned here. And the problem that occurs in behavioral synthesis is that the verifications verification. The all theoretical part related to verification in behavioral synthesis is mentioned in this in this paragraph. You can as easily check it out. Okay, so this one in your Neil West book, this one is your behavioral synthesis part. Some terms are given here, such as in behavioral compiler must perform the following operation. Behavioral compiler must perform the following operations that is mentioned here. First is it decide upon and assign resources based on the area and timing requirement. Second one is insert pipeline register to achieve timing constraint, create microcode and control unit. Okay, the area constraint, these are the main limitations. That behavioral synthesis is not able to fulfill properly. So to understand this behavioral synthesis, one example is given here. This one is in the form of simple language, that if any variable a is there, and in next step this a is multiplied with some bc terms. So we provide so after it provide into some bit serial multiplier. So for this type of multiplication instruction, if we done program in behavioral synthesis, so we have to write the program in this type of C++ type coding. Okay, so in behavioral synthesis system currently provide very good silicon implementation for narrow classes of program, and will continue to gain ground as they become more generalized and commercially available. Okay, so this one is all about the behavioral synthesis. Okay. Now the second process, the second type of synthesis process is RTL synthesis. Now, what is the mean of RTL synthesis? RTL synthesis is very easy to understand. RTL synthesis program takes a RTL description. Now, what is the mean of RTL? RTL stands for register transistor logic. RTL stands for register transistor logic. Okay. In this type of synthesis, the description is captured using the HDL language. Now, what are the different HDL language we have? uh, First is VHDL, and the second one is Verilog language. Okay. That the language or the keyword that we used in Verilog, and the language keyword and the keyword that we used in VHDL. These are almost same, but there is some difference in their keywords also. Okay. So in RTL description, commonly the RTL description are captured using this hardware description language, that is HDL. In general, this RTL hardware description language have to capture the following attributes of the design. It means that when we want to design an integrated circuit by using the RTL synthesis, at that time its programming must contain these following attributes. First is control flow using if then else and case statement, iteration, hierarchy, word width, sequential versus parallel operation, register specification, arithmetic logic, and comparison operation, all of them. Okay. I think you all aware with the VHDL language and the Verilog language. In that for designing of any integrated, so for designing of any purpose for any type of algorithm, first you have to write the code in terms of VHDL language. The any For any example of HDL language is shown here. In that, some package type and types are mentioned here. Okay, this one is nothing but a VHDL language. So in RTL synthesis we represent the all the operation of the circuit by using the HDL language. And in this RTL language, that there is no time constant, so we can easily provide the timing operation. We can easily simulate this type of RTL program also. This one is all about the RTL synthesis. So this one is all about the RTL synthesis. In this the program in the starting part, the program is written in the VHDL language, with some timing constant and simulation. And by using the all this, you can implement or verify the yes one more advantage of this RTL synthesis is that you can implement the circuit, provide the timing abstraction, and also you can verify the circuit as well. So this one is all about the RTL. So this one is all about the RTL. In that you will provide some VHDL language. In that you will provide some VHDL language for your required operation. Now, the next one is logic optimization. Now, what is the mean of logic optimization? Logic optimization is very easy to understand. Because we know that when we want to implement any circuit, so first of all we need to provide some input into it. So input can be in the form of logic expression, or it can be in the form of netlist also. It can be in the form of a logic expression, or it can be in the form of netlist also. Netlist is nothing but a programming description. Netlist is nothing but a description of the input and output, and also the connectivity of the circuit by using some programming language. The designing flow in logic optimization is shown here. This one is the logic optimization flow. This one is the logic optimization flow. It can be easily understand by taking some examples. Suppose we need to design a one bit multiplier. Suppose we need to design a one bit multiplier, and for designing this one bit, we can, by using the hardware description language, we implement a netlist and verify the circuit. We implement a netlist and verify the circuit. But when we are going towards the layout level, or for the hardware implementation of this circuit, at the time we got some limitations, that the area of the circuit is very high, or the timing or the propagation delay is very high in the circuit. So at that time we are moving towards the logic optimization. So at that time we are moving towards the logic optimization. Logic optimization is nothing but a optimization of the circuit according to designer's requirement. Logic optimization is nothing but a changes in the circuitry according to designer's requirement. That means it can be in the form of area, it can be in the form of area, it can be in the form of timing. Suppose in any designing or layout operation, the area is the main concern. So at that time the designer moves towards the logic optimization. The designer move towards the logic optimization, um, verify the circuit, provide the routing operation, verify the circuit again and again, and try to minimize the area that captured in their circuit. So logic optimization is very necessary. Logic optimization is very necessary, and very necessary to implement the hardware model of the circuit. Generally, the logic optimization system divides the problem into two stages. Generally, the logic optimization system divides the problem. Generally, the logic optimization system divides the problem into two levels. What are these two levels? What are these two levels? First is that a technology dependent phase in which the logic is optimized according to algebraic or boolean technique. And the second one is that a technology mapping phase, which translates the technology independent description derived in the previous step to specify library standard cell, FPGA element, or other implemented logic cells. Okay, so our typical flow through the optimization script is as follows: a network organization, two level minimization, algebraic decomposition, and the iterative improvement. These all are done for the for providing the better hardware requirement for the circuit. Okay, hardware requirement of the for the circuit according to demand. Clear? Suppose one example is given here. Suppose there are two functions that is given here. First is there is two functions that is given here. First is f1. First is this one, f1 equal to aef plus beg plus ceeg, and the second function is that aeg plus bg plus def. These are the two functions that we have to implement. So we know that we can easily implement these two circuit by using this 1 2 3 4 5 6 1 2 3 4. By using these four adders, we can easily implement these two functions. But if the main constraint is speed, so that what can we do? We have to modify this logic expression. So here in first function you can easily see that the ef is the common part, so we can implement it into by using some other integer, some other variable as t1. We are taking ef as a common element and represent it as t1. Okay, and the second function, when we are moving towards the second function, so you can easily see that ef, we represent ef by using t1. So in second function ef is also present, so we represent the t1, represent the ef that represent in the second function by using this t1. Okay, we represent t1 as ef, you already seen here. Okay, now there is also some possibility of minimization. What is that? There is also some possibility of minimization. You can see You can say we can also take some other variable also. We If you are taking EGST2, if you are taking EGST2, so this T2 is depend so this F1 on this F2, this F1 and this F2, these two functions are totally dependent into each other. And uh, because we are taking because we are taking EF as a common element and make it as variable T1, so it will definitely speed up the process. So in logical optimization, we are just modify this type of modify the logic functions according to the requirement, according to the area constant, according to the timing constant. We already discussed it in our this lecture. Okay. Suppose one there is one more example is given here. Suppose three logic gates are connected here. So instead of using three different gate, we can implement it by using simple gate. Instead of using three different gate, we can modify it into two logic gates. So when we implement the same logic functions by using the minimum number of gate, so definitely it will minimum number of gate. So definitely we reduce the size, we reduce the chip size, we reduce the area. Okay. Some more functions are also given here. Some more functions are also given here. These are the function here. All we you can implement, you can easily see that there is some form of mapping is done for minimization, for the minimization of the circuit, minimization of the circuit area capture, that is area captured by the circuit, minimization of area that is captured by the circuit. Okay. Okay, now the fourth level of synthesis is structural to layout synthesis. Structural layout is nothing. It is mainly divided into two or three types. First one is the placement. What is the meaning of placement in structural synthesis? First we done placement. Now what is the meaning of placement? We know that for designing of any RTL synthesis, for designing of any logical expression, for implementation of any logical expression to the hardware level, first we implement its logic gates. First we implement its logic gate in a certain position in the hardware. So the implementation of logic gates or transistor in a certain position in a chip is known as placement. In a placement. Okay. For this placement, various type of algorithm can be used, such as mean cut algorithm. Along with them, several other type of algorithm is available as well, that can be used to minimize the placement. Second one is routing. Now what is the mean of routing? From the above step, we implement the different hardware into a circuit, we implement a various element into a hardware of the integrated circuit. Now in the second step, we provide connection between one element to the another element. The connection of one element to the another element, the one element to its neighbor element, is known as routing. This routing For providing this routing, there are to provide this routing, there are the various type of algorithm that can be used. Out of them, some is maze routing, greedy routing. There are some more algorithm that can be used to for the routing purpose. One structure is given here. Various elements are connected. This rectangular part represent the size of the integrated circuit. Here some inverter register and other elements are connected. So in placement phase, first we situate the all different element into a particular position in the integrated circuit. Then in second phase, that is routing, we connect one element to the another element. In this routing rule, in this routing phase, in this routing path, you can easily see that here one register is connected with this inverter, here the N2 ND2 is connected with this register. So this one is all about, all about the standard cell layout style. And at last the last one is layout synthesis. And at last the last one is layout synthesis. At last the last one is layout synthesis. Now what is the mean of layout synthesis? Layout synthesis is nothing but a physical or geometrical geometrical representation of integrated circuit. Okay. It means that when we implement the layout of the previous, from the previous synthesis level, so here the designer need to select the design need to select the width of the transistor, height of the transistor, the diffusion or the power of capacitance that we used here, supply, VDD, and ground. The whole phase, the whole transition phase, the whole implementation phase is done in this layout level, in this layout synthesis. Here suppose we done the structure in synthesis in the transistor level. It means that we implement the whole circuit by using the transistor and transistor only. So before starting it's a physical implementation. First we design the transistor circuit. So transistor is of two type, one is N type and then another one is P type. So first we form the width of N channel MOSFET, then we have to form the width of P channel MOSFET, then we have to select the length as well. So by using this layers design, we form a transistor. Provide some interconnection to form the gate, provide some interconnection, provide some polysilicon layer to connect the gate. And then we make metal layer to provide the connection of outer atmosphere with the inner circuitry. For this we provide some metals layer. So this all process is done in this layout synthesis, Here you can see in this netlist example, everything related to metal poly, every specification of metal poly, etc. is given here. Here you can easily select the width of the poly layer, width of the metal layer, as well as the diffusion layer, diffusion layer height and width of the well, etc. You can decide in this layout level as well. So this one is the some example of netlist that we used in the layout synthesis for the designing of transistor, in the basic as a basic module. Okay, so at last after designing the layout of any at last of the designing of layout synthesis, the designing of any gate is look like these. There are some examples of layout structure. Here W represent the width and W represent the width of the circuit. Three different structure that is designed in a layout synthesis, that is designed in layout level, is mentioned here. So this one is all about layout synthesis. I hope you understand all these synthesis part as well. So okay, thank you so much.